How's everyone? Thank you for coming. How was lunch? How are the cookies? How is the coffee? Okay. This is real hardware hacking for 30 Singapore dollars or less. I'm happy to be here. This is my third time to Singapore, all within the past year. I was here last year for InfoSec in the city. And last year I was talking a little more high level and diversity of like hardware related topics. So this time I decided I'd go a little more straight down to earth and like hands-on, like what to do. Some techniques that I use on a daily basis, all wrapped up into one presentation to kind of show off some of the techniques that I use. So, for those of you who do not know me, I'm Joe FitzPatrick. I'm an electrical engineer by training. I've been spending over 15 years doing hardware and hardware security stuff. I spent 8 years working at Intel Corporation, doing both debug as well as product security for server and desktop CPUs. That kind of led me into the path where I was teaching a lot of people how to look for security bugs in hardware, which is very similar, but also has some unique characteristics to what we do when we look for security bugs in software. For the past 7 years, I've had my own business where I've been doing hardware security training. I teach classes on embedded systems and how to break them, as well as how to design embedded systems and silicon devices a little more securely. And this is what my job is. This is at work. This is at a Kaspersky conference a few years ago. I do actually own white shoes full of LEDs. I don't have them with me right now, but they're part of my normal work attire. So who's seen this device before? This is a bus pirate. So I don't actually recall at this point when the bus pirate was first designed and used, but it's been over a decade where this has been, for many people, the go-to tool for all of your hardware hacking needs. And this is a great tool because what it was is 10 years ago, 15 years ago, if you wanted to buy a logic analyzer, you had a couple low performance options, and then you had really expensive benchtop equipment to deal with. But the bus pirate was this kind of universal tool. It was based on the device right in the middle. Oops, let me change the color so you can see that. This device right in the middle was a PIC microcontroller. And this PIC microcontroller would basically speak over these wires any different protocol that you would throw at it. So it could speak I2C, it could speak UART, it could speak SPI. There were downsides to it. The chip right here on the right is what talked to the USB port. And of course it's USB Mini, which, as we all know, is ancient and horrible and should never be used anymore. We should all use USB Micro or USB-C. USB Mini is bad. But it basically talked to this chip over a serial connection, really slow, and let you go and change things that happened on wires. So it was kind of an overall slow tool, but for $30, it was a pretty good tool for a broad number of uses. The dilemma is, over time, more and better tools have become available. And while the bus pirate is great because it can do so many different things, it doesn't do any one of those things actually very good at all. It's just passable at every one of the tasks it completes. As I mentioned before, what your alternative was at that point in time was to get one of these fancy benchtop oscilloscope logic analyzers, basically expensive lab equipment. And you might notice that you're sitting here running Windows on an expensive piece of Agilent equipment that probably costs $10,000, and you're stuck with this tiny little screen and a bunch of buttons that you need to read manuals and take a class to learn how to use. So this isn't really something useful for hardware hacking, which is generally the process where we've got equipment, we want to get into it, we want to use the simplest, quickest, even most cost-effective approach to get at the hardware. Another tool that came around in the recent past is the Soleil Logic Analyzer. What this is instead of sitting there with this benchtop piece of equipment that cost $10,000, you're dealing with a piece of equipment that cost about $100. $100, and 120 Singapore dollars perhaps. And these great tools are great. They're small. This is about 25 centimeters on a side. Maybe 30 centimeters on a side. Tiny little device, you can fit it in your backpack, you can take it with you when you go, hardware hacking on the train, on the bus, in the airplane, wherever it is that you find yourself encountering hardware that you want to start messing with. What this device does is it has a bunch of little wires you can connect to your system and you can listen to what's going on. Again, we're still talking about pretty expensive equipment and pretty specialized equipment for all the tools that we want to do. So I've been dealing with this little board for the past several years, and I kind of love it. So that's pretty much what I'm going to talk about for the next hour, is how much I like this little board. It's based on a chip called the FT. Can you see? Let's pick a better color that you can see better. FT232H. And that's also hard to see. Can you see that well enough? Good. So the 232 you might recognize from RS-232. This is the old name that a lot of serial protocols used. And what happens is this device was made by a company called FTDI, hence the FT. So we have FTDI's 232, but then this H at the end means high speed. Let me high speed. And what that means is instead of just speaking TX and RX for a serial link that's going to talk at like 100 kilobit per second, this device can talk on up to 8 wires, and it can do it up to 30 megabits per second. So we have a lot of input and output of data that we can use this little board for. So you can get these boards in different finds. This is the one that I use. It's made by a company called Adafruit. It's about $15 US when you buy them directly from Adafruit. If you wanted to go really cheap, you can go to AliExpress, and you can find this for $7 US, which is even cheaper. I really don't like this board because it has sharp corners. And it seems silly, but when you're using a board more than once over and over again, you'll realize like, oh, I scratched myself. I scratched myself again. I scratched myself again. Maybe it's worth spending a couple extra dollars to get a board with a round corner and save that money on Band-Aids, right? So in all reality, we've got this board. It does the same thing. It has the same chip inside that does all the same work. The other thing that I noted, and we'll talk about why this matters in a second, is this one has the USB connector right on the board, whereas this one uses a connector for a cable, right? And it's mini. It's not mini. It's micro, so it's okay. And this means that we can put this board right next to our target system and run a long cable to our computer, instead of this one where it has to be stuck to our computer and we end up with long wires coming out of the side to connect to our system. We want our wires to be as short as possible. So this is in SimLim Tower. You can go there and you can buy these, and it's actually the only time I have ever seen one of these devices on a rack in a retail store. In the United States, we've got Micro Center and Fry's Electronics, which are ones that actually carry a lot of Adafruit, these little blue boards, this brand, Adafruit boards, but they often carry the more common ones, but they never have carried this one, the FT232H. So I was really excited to see that, and that's $28.90 Singapore dollars. So yes, they're there. This was the last one on the shelf, so you might have to wait, but so I'm going to talk about actually I have 8 here, 8 different approaches to what we can do using this little board to help us with our hardware hacking. Okay, I'll go through each of these, tell you what tools I use, how I do it, how you can do it, and then give you a short example. So we can use it as a logic analyzer with a tool called SIGROC. We can use it as simple UART console, like a regular as a regular RS-232 communication device. We can use it for JTAG control using a piece of software called OpenOCD. And then there's a tool called FlashROM, which is specifically designed to talk to flash chips. And we can use it for both dumping the contents and writing back new contents to a flash chip. And finally, we'll look at a couple other neat features we can use, like talking I2C, which is yet another serial protocol, as well as making our own crafted packets for any proprietary protocol that we wanted to make up, or that a manufacturer made up thinking that they would protect it from our eyes because they used a non-standard protocol, which doesn't work. So FTDI LA, so the company is called Future Technologies Device Incorporated, and LA for Logic Analyzer. This is a driver for a program called SIGROC. And so what I'm going to do is I'm going to take this little board right here, and I'm going to hook these rainbow cables up to a Raspberry Pi I've got sitting right here. And this Raspberry Pi, like every Raspberry Pi, has what's called a serial console on it. It'll spit out some text over one wire. And what we want to do is we want to figure out what pin those are on. We could just look at the data sheet, but data sheets are kind of hard to read through. They're complicated, and then you have to find the right pins, and sometimes you get TX and RX mixed up. So the easiest way is to just hook up a logic analyzer and observe, right? So what we can do is we can use this tool called SIGROC, and it opens up and it's a logic analyzer. What we see here is we have our different pins right? So we have TX and RX. These are the communication wires that the serial port's going to use, as well as a bunch of other control signals that no one really uses, so don't worry about that stuff down there. And what we see very quickly, we see there's not much happening on this line, but over here we have a lot of gray stuff. So something's happening. Let's look really close to see what exactly is happening. When we get down to it, we see that this is a signal that just goes up and down a lot, right? Those up and downs are the ones and the zeros that are getting transmitted by this protocol, right? So once we've done this, we know that black wire is connected to something that's got some data on it. We can look at the size of these pulses and it'll tell us what speed it's communicating at, what baud rate it is, right? And we use that information to go and analyze the data that's going on that protocol. So PulseView and SIGROC, these are open source tools that work with the FTDI device, will let us go and do some software that'll decode the bytes that are coming across the signal down here. It's pretty neat. So the first way we can use this device to go analyze a system we haven't seen before. The thing is, a logic analyzer is designed to listen to a bunch of signals. It's not designed to communicate back and forth. So we need another tool that will do that. So again, if you want to use PulseView and SIGROC, it's open source. SIGROC, S-I-G-R-O-K, like SIG signal, and GROC to understand, so understanding signals. PulseView is the open source GUI interface to it. So you can use SIGROC on a command line, which is pretty cool if you want to hook up a bunch of devices and capture them. You just run a single command line, and it's really good for scripting. Or if you want the interactive mode, you get PulseView. And it's available for like pretty much every operating system. There's even an Android version, which is pretty cool. The Linux one is the most stable and where all the development happens. But you can install it on Ubuntu, just apt-get install SIGROC and apt-get install PulseView. And you've got a pretty awesome logic analyzer software. I teach a lot of classes, and in my classes, up until very recently, I used the Salier logic analyzers, which come with their own software. But that software hasn't changed and evolved very much in the past 5 years, whereas PulseView has come a long way, and actually it was, just last October, it had the last major revision, had a couple features in it, so it's basically feature complete for me. This is what I use for my own work, and it's also what I'm going to be using for my classes in the near future. And again, you can use it with these FTDI boards, and I'll show you a picture of some other logic analyzers we can use with it as well. So next, we saw using the logic analyzer that we had some data being spit out. Let's go and communicate interactively with that data. So what do? We hook up those, did I have a picture of the wiring? I guess not. We hook up those wires, pretty much the same wires on the same pins of that Raspberry Pi, and we tell it to go and talk to the Raspberry Pi at a baud rate we know. Have you heard people talking about like 9600, 8N1, right? That 9600 is how many bits per second, and then the 8 means you have 8 bits per byte, and N means you have no parity, and then 1 means you have 1 stop bit. That tells you details, about the electrical protocol that's coming out. So what we can do is we can use a tool to go and talk to this little blue board, which is then going to go and talk to the target system. So what do we get on the other end? So the example we've got here, we see, okay, we're uncompressing Linux, we're initializing things, we have memory, we have a Raspberry Pi, we have some virtual memory layouts. This is the boot log of a system that's powering up, right? As it powers up, it's going to tell us all sorts of things about what's running on it, what storage it uses, what drivers are installed, what devices are attached. This is all really useful information. It's not the only information we'll get off of a device. Some things we might encounter, the boot log, okay, that's great. But that's not interactive, that's just informational. Sometimes we hook up a serial console to a device and we get a management interface, right? This will be like on switches and routers. You hook it up and you say, hey, what would you like to do? Would you like to load configuration, dump configuration, modify system settings, reset router? That kind of management console doesn't give you a full control of the device, but it gives you a little bit of leverage onto what things are running and how they work on the device. Now, what I like to see is more down here. What happens when we finish booting up? We get the whole boot log, and then it says login. Like, okay, this is really helpful if we know username and password that we can use to log into a device. But that's not an easy thing to figure out just by sitting there on the login prompt. Fortunately, unfortunately, a huge amount of the time you go straight to a root shell. You plug in 4 wires to a board, you power it on, and you get a root shell. Who likes root shells? Who likes hard shells versus soft shells? Who likes tacos? Okay. So root shell. So we get a root shell and we're there. This is kind of like when it becomes a software thing. So I'm a hardware person. I like to use my skills to hook up to the hardware and make hardware do things. Once I get to a root shell, that's something that I can hand off to a software person who knows a lot more about software than I do. And that's kind of when it becomes someone else's problem too. So let's talk though, like what if we had this login prompt? We didn't get to a root shell, we need to log in, we need to figure out what a username and password is. Is there any other approach we could use? So before we dive into that, some of the commands you can use to do this on a Linux box. So screen is the one I use the most. Screen is a utility that has other purposes, but what I use it for is speaking to serial ports. This TTY USB 0 is the device that appears when you plug a USB device, when you plug this little blue board into your system. And you can also use another tool called CU. It's kind of an older, clunkier tool from an older time. Minicom is kind of I would say the cool new thing that the kids are using, but it's still console-based, so it's not web-based, so maybe not everybody's using it these days. But anyway, it's got more interactive display where you can change baud rates and change settings in a more GUI interface. So if you like Vim, then you'll like Screen. If you like Nano or Joe or Pico, you'll like Minicom better. Does that make sense? And I put these in here for you, James. Maybe you could use PuTTY or Hyperterminal, right? Because if you're stuck on a Windows system, So, actually, I hopped out a little bit out of order. So let's talk about OpenOCD and JTAG. Who's heard of JTAG before? So JTAG stands for the Joint Test Action Group, which is an acronym that doesn't really mean anything to anybody. But it's basically a way to interface to debug control, to control debug on a lot of systems. Who's used GDB before? GNU Debugger? Or any of WinDebug, or who's used a software debugger to go walk through your code as it runs? Well, the same thing you can do from a hardware perspective. Instead of latching onto a process that's running on a system, you latch a bunch of wires onto your target platform and send a bunch of ones and zeros down those wires to go and control what actually happens down there. OpenOCD is this open source tool package that helps you do that. There are closed source applications that'll do that. There are companies whose business is essentially to make JTAG interface tools. Some of them are very product specific. They only work on one certain manufacturer's products. Some of them are very broad. So Sega or J-Link, they make a software that works for hundreds of different ARM processors just by configuring them slightly different. OpenOCD supports lots of ARM processors, lots of MIPS processors, and a handful of PowerPC and x86 processors, but mostly ARM and MIPS. It's really handy. I like to use it because it's free. I also like to use it because it works with my $15 JTAG adapter instead of having to work with a $100 or a $20,000 JTAG adapter. Yes, $20,000 JTAG adapters do exist, and people pay that. I don't know why. Anyway, so ARM and MIPS. So let's see what happens. We'll hook this up to the Raspberry Pi again. So we had to do a little configuration on the Raspberry Pi to put it in JTAG mode. But once we've done that, we just have to hook up the right wires to the right pins. And handy enough, the Raspberry Pi has all of the JTAG pins exposed on that nice row of headers right there. So once we do some magic, figure out which pins are which, we won't talk about that here because that involves data sheets and it gets messy. We can then go and start the program OpenOCD. We tell the OpenOCD program to use our FT232H config file, and we also give it a configuration file specific to the Raspberry Pi, right? That tells it that it's an ARM processor, has one core, and it has, I forget, 256 or 512 megabytes of memory. And OpenOCD will see that information, and it'll go and say, okay, we found our device, we've got a clock speed, we've got an identifier that the Raspberry Pi gave us that says it's a Broadcom CPU. You're all set to go. It's ARM 1176. You have breakpoints and you have watch points. What would you like to do? Right? Now I said the whole point of this is we get debug control of the device. For that, we can use good old GDB. So this is actually a specific build of GDB. It's GDB, let me write those letters properly, GDB multi-arch. And this is handy because GDB is specific to whatever architecture you have it built for. GDB multi-arch is basically someone who went and compiled GDB with support for ARM, MIPS, x86, x86 64, ARM 64, all these various architectures all in one single GDB executable. So what we do with GDB multi-arch is we say, okay, we have to very specifically specify that our architecture is ARM, and then we're going to do a target remote localhost 3333, and this is what connects to OpenOCD. OpenOCD, right? Once we've done that, we've got a debugger. We've got a debugger prompt, and we can do things like this. I did x10i and then an address. x10i means display 10 instructions at the address of C0136DD4. I'll tell you how I figured that out in a second. But what we see here is we see some ARM assembly. And if you're familiar with ARM calling convention, we have a push instruction right here, which is going to push a bunch of registers to the stack, followed by the program counter, right, which is going to be like the return value to when we pop it all off. Pretty cool, huh? So this is how we go ahead and look at code. We're looking right here at a function in memory that's part of the kernel running on this Raspberry Pi. The way I got this C0136DD4 address is I basically had the serial console on the Raspberry Pi, and I asked it to give me a list of where all kernel functions are. So this is actually a function called generic permission. This is a function that controls whether you have permission to access a file or not. If I have access to generic permission, and I can go and like watch these instructions happen, I can watch things get pushed on the stack, I can also watch things get popped off the stack when the function ends. And how do functions tell the calling code whether they were successful or not? Anybody? Return values? So in assembly, that's often a specific register, and I can never remember one from the other. I believe R0 in ARM is the register that's going to hold the return value. If you ask to access a file, and you have permission to access that file, generic permission will say true, you can access it, 0. If you do not, it'll give an error code. In this case, it's -13. So all I have to do is go and step through this code until I'm about to return to the main program, and I just change the value of R0 to 0, and I have bypassed that permission check on the system. So that's how I can use JTAG on a hardware system by hooking wires up to go and control execution and dictate what it's going to run. So first, the tool OpenOCD. Again, I'm writing with a white marker on a white line. So OpenOCD is the first tool, right? We need to give it some configuration files. One that tells us how to talk to our JTAG adapter, and then another one that tells us how to talk to the Raspberry Pi. These are just text files. They're pretty straightforward. It can be difficult to build these configuration files if you have an unknown target system, but many targets have already been defined, and you can find configuration files for them already. Then the tool we use to talk to OpenOCD is this GDB multi-arch, right? Again, GDB is a debugger. This is the exact same program that we would use to attach to a process and debug the process and halt the process and set breakpoints and watch points in the process. We can do that on a local system on the process. We can use the same exact tool to do it remotely over OpenOCD, over those wires to a target system, right? So it's pretty cool, because I can run this on my laptop and use it to debug the processes running on my x86 laptop, and the same executable, I can run it on my laptop, connect it to a JTAG adapter to debug processes and the operating system on the Raspberry Pi itself. Pretty cool, huh? So once we get into GDB, we have to go and set that up properly. The first one tells us we want to talk to an ARM processor. The second one tells us to talk to OpenOCD, OpenOCD, which is the program that's talking JTAG. And then lastly, we give it the commands to let us look at the contents of memory that we want. We could also use the set command, and we can set R0 equals 0, right? We set our return value to 0, and tell OpenOCD to let the processor keep running, and that's how we can bypass a permission check on a function. Sound good? So let's say we didn't want to go all the way down the path of OpenOCD because JTAG can get pretty complicated. We need those configuration files. But we do have a system that happens to have flash for a firmware, right? So when the system powers on, it goes to a flash chip, it reads some code out of there, it executes that code. Sometimes it's bare metal firmware, it's just code that directly executes. Sometimes it's in a full operating system, so it loads a bootloader first, and then that bootloader loads a kernel, and then that kernel boots up and mounts a file system, and all that stuff could be stored on one little flash chip. So wouldn't it be great if we could look inside the contents of that flash chip? So we'll use flash ROM. which is a pretty popular tool for looking at dumping flash out of things. You can actually run flash run on your laptop or your desktop computer, and it can go and actually dump the BIOS off of your CPU, off of your computer, because it's actually the same chip speaking the same protocol. You can also hook up one of these little FTDI boards to a target system and also use that. So what we see here, we have my little blue board up here. This over here is a Wi-Fi router, and if we look and zoom in, we can see this little chip right there. And that chip right there is our flash chip. It's an 8-pin flash chip. It has 8 megabytes of storage, which happens to be just enough to store a kernel and a root file system for an embedded Linux operating system. It's an OpenWRT-based system. And what we did here is we got these probe clips and clipped them on to the right pins. And how do we know the right pins to talk to? What if we didn't know what pins to talk to? What tool do we have that we can analyze and look at things? We have a logic analyzer, so we can use SIGROC and PulseView to look at the pins. We can hook up clips to all these pins and watch the whole thing happen. We'll be able to see the system boot up. We'll be able to see the bytes and the files run from the flash chip into the CPU. Once we've figured that out, then we can go and figure out which pins are which. We could also look at the datasheet for this chip. It's pretty handy because manufacturers of flash chips, they always want to make their chips to be most versatile, most flexible. So they have pretty much all ended up using the exact same footprint. So the same 8-pin chip from any one of a dozen manufacturers is all going to work almost exactly the same. So if I'm building a Wi-Fi router and today WinBond chips are cheaper, I'll buy WinBond chips. If tomorrow Spansion chips are cheaper, I'll buy those. And if the next day the Atmel chips are cheaper, I'll buy those. Whatever chips I want, I can buy and put them on the board, and they're all going to work the same way. I can look at the datasheet for any one of those chips from any one of those manufacturers, and it'll tell me the right pins. And it happens to be pin 1, pin 2, pin 4 is ground, and pin 5 and 6 over here are the important ones. And then we have a power pin up there on 8. So we hook up our probe clips to this thing, and now we've got to open up our tool. The tool, again, is FlashROM. We're telling FlashROM we want to use the FT232H. Unfortunately, this is kind of an older tool with a very esoteric command line interface and parameter method. But basically what we're telling it is we want it to talk to a FT232H, so it'll look on your system, find an FT232H, and it's going to read whatever it finds on the other end and put it in spydump.bin. And sure enough, FlashROM, because it's open source code, it's still sitting there at version 0.9.9, release 1954. And I'm sure that version 1.0 is going to come any day now. But I mean, we've been on version 9.9 for about 5 years, so I'm not staying up late at night waiting, F5ing, seeing where they're going to release it. But we basically find the device, we talk to it, we ask it for an identification code, and then we read the contents of Flash. And I mean, we can't really see how long it took just from this picture. It takes about 2 to 10 minutes to read the contents of a flash chip, right? All we have to do is hook up the right pins to the right spots, run the commands, and there we go. So now the next question is, what do we do once we've got this contents of these flash chips, right? So I've got this tool that I use called binwalk, right? It's written by a guy, Craig Hefner. It's pretty well regarded. When you have a file and you want to analyze what it is, you might look for some magic numbers in the file. That's like file headers that might tell you whether it's an image file or a zip file or a PDF file. Well, the problem with firmware images is firmware images aren't just one file. They're usually a whole bunch of files clumped together. So sometimes they're concatenated to each other. Sometimes they're compressed into file systems. binwalk knows a lot of these magic numbers and patterns that it's looking for in files. And so binwalk will walk through your binary file, hence the name binwalk, and look and say, oh, when I was looking at address 17160, I found a version string that says uboot 1.1.3. Okay, it recognizes a string. It knows that it's from uboot. It knows uboot's something that's very interesting for people. It'll also look and say, oh, I found a bunch of HTML document headers, right? This device actually has like a bootloader that you hold the button down while it powers on, and it opens up a web page so you can go and upload new firmware, right? It's recovery mode. Well, all those web pages are HTML files stored on a flash chip. Now, we get further down and we see we've got a uimage header, right? This is a header for a Linux kernel. So on this system, we have some compressed data as well. That compressed data is the kernel itself, compressed. right? And then last, we've got a couple file systems, SquashFS and JFS2. Each of these, at this offset within the file, are existing there. So we've got a tool that's going to walk through and recognize all the components of our firmware. So once we've done that, we can actually, binwalk is pretty handy. It's got this other option, -E, which is extract. And basically it says, well, if you know that you have LZMA compressed data, then why don't you just use the LZMA tool to decompress it? If you know you've got a SquashFS file system, why don't you use unsquashfs to extract it? Well, so you do the -E and it does that all for you. And then you can go and browse the system and you can look at all the files in the system. And this is just one file. This is etc init tab. And this system, when I was playing with it, I found out every time I power it on, I see a boot log, and then it automatically logs me in as user. And user isn't that much fun because user is just a plain old user. They can't go and access all the files in the system. What user would you want to be? Root. So I look through and I find this etc init tab. This is the list of commands that get run during initialization. And right here, there's this ask console command. And when you want to get a console, whether you connect to it or you hook up a serial console, it says, oh, all you got to do is run bin login -f user, right? So what this does is it logs in a user, and -f means don't bother asking for a password because we just want the user to log in. Well, what happens if I modify this file and I say login -f root, R-O-O-T, right? That should be pretty handy, right? That means when I boot up the system, this file will tell it to log in as root, and I'll get a root shell. But this system is on my laptop, decompressed and extracted, so I have a little complicated, missing a slide. I got a complicated process where I actually have to repack the firmware, right? I extracted it with binwalk. Now I modified a file, and now I need to make a new file system, make SquashFS, and there's a lot of options you have to deal with when you do that. You repack it, and then you can flash it back to the system to get it to run. And sure enough, here's a picture. I used flash ROM. The command line is almost exactly the same, except instead of a -R, it's a -W, right? Same process is happening. I have my tool flash ROM, which talks to my FT232H device, which is that little blue board, over those wires to the flash chip, and it goes and tells it what bits to write instead of what bits to read, right? Once I've done that, it'll go, and actually it's kind of annoying, because first it finds the chip, and then it reads the old contents, and then it writes the new contents, and then it reads the new contents to make sure it worked, which is really annoying and slow, especially when it takes 2 to 8 minutes for each of those steps. So it could take up a half an hour, which is really, really, really annoying. But it happens, so it's reliable. Just let it do its job. So the tools we use flash ROM to both read and write to this flash chip, right? We tell it to use FT232H chip, and we tell it the file we want it to extract to store it to or write it from. We use binwalk to break it up into pieces, and then we use make SquashFS and DD to go and repack it into a file that we can go push back to the system. Is this all making sense? So, again, we're going through all these different techniques, and while we do have to have a target system to work with, in terms of tools, all we've used so far is one tiny little board that we can get in SimLim Tower for 28 Singapore dollars, which is a pretty good deal, don't you think? So now I'll give you a couple more examples of things you could do if you had specific systems that needed them. One of them is speaking other protocols. I2C is one particular protocol. So there is a library called libmpsse. MPSSE. And MPSSE, I can't remember exactly what it stands for. It's FTDI's high-speed API to talk to this device. And basically, this is a library that you can use from C programs or from Python to go and control at high speed all the pins on this board. So you can write software to implement protocols. So here we go. In our example, we basically import the MPSSE thing, library. And then what we can do is we can basically go and set pins high and set pins low, right? Turn them on and off, right? So if you think about it, how many of you have ever played with an Arduino or Raspberry Pi? Has any written any firmware where you basically want to flash an LED, right? So it's kind of like the hello world of hardware, right? You flash an LED. If you can flash an LED, you can turn it on and you can turn it off, right? Well, just like hello world, if you can write hello world, then it's not a big difference between writing hello world and writing HTML headers and writing PDF files or anything else, right? Well, same with LEDs. If you can flash an LED on and off, that's making a 1 and a 0, a high and a low voltage. It's just a matter of combining them in creative ways to speak more advanced protocols or control motors or centrifuges or anything else you want to do. So once we've done this, once we have this way of writing Python code to do our 1s and 0s, we basically have all the tools we need. So what we can do is we can bit bang a custom protocol. Who's heard this term before? So bit banging, what we're doing is we're basically thinking of the protocol as a bunch of bits, a bunch of 1s and 0s. When we want to do a 1, we write a line of code that says output 1. When we want to do a 0, we write a line of code that says output 0. Sometimes we'll have a fancy protocol which has multiple wires at the same time. So in this example, we have a clock, and then we have data. And what happens is basically, every time the clock goes up, we have to make sure the data has a value. So here, the clock goes up, data is 1, clock goes up, data is 0, clock goes up, data is 1, right? So it looks kind of complicated, but what we have to remember is we just have a bunch of 1s and 0s. So what we do is we write a command right there to output 1 on a clock. Write a command right there, output 0 on data. Write a command there, write a 0 on clock. Write a 1 on clock. Write a 0 on clock. Right? So this is all software that's able to control these 1s and 0s and spit out this protocol. So here we go, and this is actually the library that's implementing the I2C protocol, which is essentially bit banging it. So we say, okay, we want to use MPSSE in I2C mode. We're going to go and we have written a bunch of library software that's going to toggle 1s and 0s and send little packets over the wire. A start packet, we'll send a write packet, we'll wait for an acknowledgement, which is reading, looking for 1s and 0s instead of speaking them. And then once we get the data off there, we can write an acknowledgement back. So again, when we write the 1s and 0s, we're writing at the lowest electrical level, like the data link layer protocol, if we think of the OSI 7-layer model. As we build up, we go to a transaction layer protocol, where we have a protocol that we send bytes and we get bytes back. And then at the highest level, we'll have the whole functionality. We have a device that happens to be a temperature sensor. So we go and read the temperature, and we get data back, and we do the math and convert the value into reading in Fahrenheit or centigrade or whatever units you prefer to have your temperature in. So this is using libmpsse. It's a software library. It works with C and it has bindings for both Python and a few other scripting languages, which is pretty handy. It's all on GitHub. Although it's actually, I don't think it's been updated in 5 or 6 years, it still works just fine. There are a couple people who have done more later versions, but none of those changes have been pulled back into it. But fundamentally, you're dealing with hardware. The hardware hasn't changed in the past 5 or 6 years ago, so don't worry about it too much. So in the last few minutes, I want to talk a little bit more about the tools that you might use. So this is the one that I talked about and used in all of my examples. The reason why I chose it is because it's readily available. I can find it in a store in Singapore. I can find it in Manhattan where they make them. I can order them from DigiKey, which is a, what's it called? A distributor, component distributor that I use a lot in the United States. But it's great, it works, it does the job, they're inexpensive. There are several devices that use the exact same chip. And I've used each of these for different purposes. So this is the one over here that I use most of the time. This is what I use in my classes. I get them when I buy them in quantity for between $10 and $15. Of course, if you get them in a store, they're going to be a little more expensive. This one over here, let's go up to this one in the top corner right here. This one is got a strange name. It's called the TUMPA. And I don't remember what that stands for. This is a manufacturer that sells a lot of mod chips and other phone jailbreaking devices from several years ago. And this was their all-purpose device for doing JTAG stuff on phones. I never actually used it for the manufacturer's intended purpose. I just used it because it had the chip that I wanted to use inside. My experience was that they actually had a high failure rate though. I don't know why, but they just kept dying when I was using them for class. So that's why I moved to the Adafruit one. The one on the bottom right is a more recent one. It's made by Exodus Intelligence. They teach a class on embedded exploitation, and they made this cool little board that they give out to people who take the class. And I want to buy them, but they said just take the class. And I have my own classes to teach, so I didn't want to take a class just to get a board, but they gifted one to me. What I liked about this one is it had all the headers for common pinouts attached to it. The other thing this one had is it's got these chips in the middle, right? So this board over here, it's a 3.3 volt device. So if I want to talk to a device that's 3.3 volts, I'm doing a great job. If I want to talk to a device that's 5 volts, it actually will probably work most of the time without a problem. But if I want to talk to a device that's only 1.8 volts, I run the real risk of burning it up, frying it. And I've done this too many times, and I admit it over and over again. And I did it once to a $300 tablet, and then I realized what I did, and I turned around and I did it again to another $300 tablet, like 5 minutes later, and I'm like, wow, that was pretty much the dumbest thing I've ever done. And I decided that since I didn't really need to do it, I didn't buy another $300 tablet and destroy that one as well. But, you know, it happens. So, you know, that's, you know, I may be talking about hardware hacking for $30, but you have to include the cost of all the hardware you're going to break, because you're going to break hardware. And it's kind of like, I don't know if anybody goes skiing in Singapore, but in skiing they always say, like, if you don't fall down, you're not trying hard enough, right? Well, in hardware hacking, if you're not breaking hardware every now and then, you're probably not taking enough risks. And that's maybe my approach and not everyone's approach. Lastly, we've got this board up here, which is brand new, and I just got it last week, and hopefully will be readily available in the near future. It's called the UNIT, Universal IoT something. I can't remember what its abbreviation is for. But what this guy, David, did is he used a similar buffer right here. He's got a bunch of dip switches right here, so you can change the voltage. You can use this on a target system that has 1.2 volts or 5.5 volts. All you have to do is switch the jumpers. And we've got headers for I2C, for SPI, for JTAG, for UART, and SWD and JTAG as well. So you got lots of really useful headers on this board. I have high hopes for this one. We'll hopefully make sure it works. I have one with me. It's the like one of 3 that's working right now, but it'd be really cool if this would be a more readily available board. So these are the options that I have and use, and here's a close-up version of the unit. And this is a hand-soldered one, so hopefully in the near future there'll be manufactured ones. But let's talk for just a minute about all the tools that we used, right? We did a white on white. Yeah, let's change colors. So we used a logic analyzer with the SIGROC tools, right? Then we did UART console access because we used the logic analyzer to tell what speed our device was talking at, and we could get a console, even if that console was not a root console, it was still useful information. We can use OpenOCD as a tool to go and get JTAG access and to control and debug the system, modify the contents of memory, right? And then we've got flash ROM. We can use flash ROM to dump the contents of firmware and then write the firmware back after we've modified it. And another tool we used here was binwalk. That would let us go and disassemble, unpack, not disassemble because that has other meanings, unpack the firmware so we can modify it and repack it and send it back. There are a couple other tools that use binwalk. There's one firmware mod tools. It's a library of tools like binwalk and SquashFS that are all bundled together to let you deal with embedded systems firmwares. And then as we go down, we can do things like messing with I2C configuration bits. And if we want to, we can go and speak a custom protocol written from scratch, written in software, but using hardware 1s and 0s and 0 and 5 volt outputs to go and actually make that happen on the target system. So again, if you want to snap, this is a picture. The screen has all the tools that we've used. Most of these are pretty searchable by the name, or if you're on Ubuntu, you can just like apt-get install. Apt install. You can apt install most of these, and that's actually every one of these, the package name is exactly that, so you should be good. And then you have, with $30 of hardware, all the tools you need to do quite a bit of different hardware hacking activities. So with that, that is real hardware hacking for 30 Singapore dollars or less. And we've got time, I believe, so if you have any questions, I can tell you more. But what we also have is tomorrow afternoon, there'll be a workshop format. And it does say hands-on, however, I don't have all my equipment with me because I didn't do a class this time. So it will be more of a Q&A, and I'll walk through demonstrations of each of these things on screen. So if you want to hear more about this, do come tomorrow afternoon to see the workshop format version of it. But any questions?
Okay, thank you, Joe, for the talk. And tea break is happening now, so feel free to help yourself to some refreshments. But come back in time at 3 p.m. for the next talk. Thank you.
Thanks. Thank you.